Okay, perfect. So cosmetics have been used in different, well, among different cultures and in different times, right? So, for example, they've been used in theaters or, for example, at courts to show off status. Nowadays, they are used, for example, in parades or to create a very dazzling look that, I mean, the goal is to actually create this look that is very flamboyant and very different that actually capture the attention and will be remembered. But the most common use that most of us know is that the goal of cosmetics is to, well, enhance the appearance of someone and then also to hide what this society regards as skin imperfection. So cosmetics are a multi-layered structure, which means that it's not just applying one single product on the skin, it's actually more than that, right? And so for the simplicity of this presentation, we just consider a few layers. So we start with a bare skin, and then we apply what is called a foundation layer, which is the goal of this layer is to create an even and structured layer in order over which it's possible to apply more layers on top of that. Then it's possible to apply a bronzer, which in this case it's applied in the cheek area, and then finally a highlighter, which has the goal of increasing the reflectance. And on top of this, we have to consider that it's possible to create different appearances, going from a dewy look, which is quite glossy, as you can see in this image here, or to a very matte one, which essentially suppress most of the highlights. In order to recreate these effects, it's quite common to apply the same product over the same patch, skin. And a phenomenon that has been observed is the fact that the more cosmetics we apply on the same patch skin, the more the reflectance is going to increase. And this has been measured in previous work. So the goals of this project are to create a parsimonious reflectance model that is able to reproduce this continuous versus dewy appearance, or this dewy versus matte appearance in a continuous way, this increase in the reflectance as we apply more cosmetics on the skin, on the same skin patch, and then finally also considering the fact that it's possible to stack multiple layers. The challenge that we had to face in this project was the fact that it's hard to find data. So it's hard to understand what are the components that actually influence the optical properties. And the reason, one of the main reasons is the fact that the companies that actually produce cosmetics are not that interested in revealing this data, right? So I'll just briefly discuss some of the previous works that have been tried and developed for physically based models for cosmetics reproduction. So there are two works that measure in vivo and in vitro cosmetics, which means in vivo it means that the cosmetics was measured on some skin patch and it was applied directly on the subject and was directly measured there. And then in vitro is a controlled setup, which is more calm and truncated and more controlled, but it's more easy to make measurements in this setup, but at the same time it's less, does not consider all the skin types. The problem is of these two previous works is that they rely on using Kubelkeman theory, which lacks of directionality and does not account for surface roughness. I mean, it's possible to account it, but the main theory was not developed to also take into account surface roughness. Another work in the reproduction of cosmetics took a different step and instead tried to use a data-driven approach. 56 subjects were the appearance of 56 subjects were registered with and without makeup, and then from this difference, the authors were able to embed the makeup into different maps, as you can see here. Although these maps allow some control, it's still limited because, for example, as I was saying before, this is a multi-layered, it's a multi-layered structure, and so, for example, if it's not possible, for example, to disentangle between the bronzer and the foundation layers. And on top of that, it's harder also to resimulate this increase in reflectance as we increase the thickness of the foundation or of every cosmetics that we apply. Another point that I would like to make is the fact that it's not, those are work that are not essentially physically based, but it's interesting to remember and to consider the fact that there are other applications, and this is not just reproduction, or that does not simply encompass the reproduction of cosmetics, but for example, other applications such as makeup transfer, makeup suggestion, and virtual try-on that mostly rely on a data-driven approach. So I'll just now start to discuss the work hypothesis and the model that we would like to propose, and then finally I'll discuss measurements and results. So we start by making the assumption, more or less, is that the cosmetics are essentially a hosting medium filled with insoluble particles, which essentially makes a colloidal system. This is a very vague and general descriptions because, for example, so it can be applied to many materials, such as milk, for example, in which the hosting medium is water and those particles are fat. So we model cosmetics as a volumetric media, and specifically we use the position-free Monte Carlo framework for this. And we also make the assumptions, or the simplification, that particles are dispersed in the air. This allows us to remove the first surface, the surface interaction. But as we'll see later, this is enough to recreate quite reasonably well reality. And then we also make the assumption that the main color mechanisms are scattering and absorption, which means that there are no wavelength-based coloration and no fluorescence and no chemical reactions. And we make this assumption, especially in class 2, based on legislation, because they are not allowed, at least in Europe. So there is no fluorescence mechanism and no chemical reactions are allowed in cosmetics. The third one, wavelength-based coloration, is allowed, but extra tests are required because it can be dangerous for you. So, as I said, we make this assumption that it's a hosting medium filled with particles, but how do these particles look like? Well, we managed to find a paper in which they actually did a scanning electron microscope pictures of some cosmetics. And we can see here some of the components that it's possible to find in a cosmetic. And you can see here silica, talc, kaolin, and titanium dioxide. The titanium dioxide is the smaller one, the one with purple squares. So this is how a cosmetic looks like when it is applied on a human, but then it's also interesting to see how these components look like when they are in their free state. And we can see here this is silica, and they are essentially the same materials of before, silica, talc, kaolin, and titanium dioxide, just in their free forms. And we can start to make the observation that talc and kaolin look like flat. They tend to be flat and polygon-like. Meanwhile, silica and titanium dioxide, they tend to have this shape that is more spherical or cuboidal. With this in mind, we essentially want to suggest, in this work we proposed to model these two different types of elements as different types of scatters. One is these diffuse scatters, representing more or less this silica and titanium dioxide, and the other ones are kaolin and talc for platelets. We model these scatters by means of the phase functions. Just a brief recap, the phase function is just the function that describes the distribution of outgoing rays when we hit particles inside a medium. A very common phase function is the Hinian-Greenstein phase functions that is widely used in computer graphics. And this function is mostly, it's controlled by just one single parameter, the parameter g, which controls the shades. Meanwhile, but more formally, it controls the average mean cosine of the outgoing direction. But what is interesting for us is that for positive g, we have a forward scattering, for g equal to 0, an isotropic one, and for g equal to 0, a backward scattering. So I've described this because we define diffuse scatters as two-lobe phase functions, meaning that we have a forward lobe and a backward lobe, and then there is a third parameter that defines the weighting. And we make this modeling based on previous works that on titanium dioxide, in colloidal systems, and also on sunscreen lotions, which, again, sunscreens are mostly based on titanium dioxide. So it seems that this is a good approximation, right? And for the platelet scatters, we rely on using essentially it's a normal distribution that follows the SGGX distribution based on previous work. Now it's possible to define this platelet in various forms, and there are different parameters, but in this work we only use two parameters, the platelet roughness alpha, which as we increase this platelet roughness, it means that these platelets are going to be bulger. And then we also have the platelets orientations. Yes. So to sum up, our model is essentially a medium with no interface, filled with two types of particles, platelets and diffuse spherical diffusers. And then we have different optical parameters. We have the albedo for the platelets, which allow us to change the color of the platelets, the roughness, as I was saying before, and then the rotation. We also have the albedo for diffusers, which allow us to define the color of the diffuse part, let's say. And then the forward load, backward load, and the weighting factor. We also have two other parameters. One is the optical thickness, and then the relative concentration of diffusers. So those are our working hypotheses and our model, and now I'll discuss about the measurements. So we take 4 samples, we buy 4 samples and we measure them. We have the first two on the left are two dewy foundation layers, and then on the right, 2 matte ones. We measure on this setup, and yes, I mean, in this image here, we are applying cosmetics on those cosmetics on a cylinder, but in reality, we measure them in a planar conditions, and we only measure the azimuthal condition. We work in saturated layer conditions, meaning that we increase the thickness of the sample up until we observe no color change in the camera, which is this last step here. So in this way, we know that we are working in multiple scattering conditions, and the underlying plane is not affecting that much the measurements that we are observing. So on the vertical axis, we have the different light conditions, and on the horizontal axis, the different camera position. And we have, those are the materials that those are the samples that I showed you before, how they look like. And as we can see, well, we have this diagonal of highlights, which is predominant of these two dewy appearances, which is reasonable. I mean, this is what we were expecting, at least. And then for matte, we have almost no highlights. So we have some data, we have a model, and what we actually do is essentially parameters fitting, right? We run an optimization, we work in using an L2 loss function, and we work in linear RGB space. And we use Powell because we don't compute the gradient. And those are the results that we obtained. We are able to match the highlights. We are able to pretty much have similar highlights for the two dewy conditions, and also the color is reasonably similar. And then with this optimization, we start to see how our model changes if we only use one type of particles. So we have in the third column only diffuse particles, only platelets, and then we use only platelets and diffuse particles, but diffuse particles are defined using a single load. So this was the measurements part, and I'll briefly discuss the results. So we have here our initial reference, which is, let's say, a bare skin. And then we apply our optimized model for using the dewy one data, and then for matte 2. And as you can see, the highlights that it's possible to see near the nose and the cheek and beneath the eye are increased. Yes, they look brighter under the dewy one conditions, and they are suppressed more when matte 2 is applied. And these are some zooms. We also explore how the parameters affect the final appearance. And so on the horizontal axis here, we change the concentration of diffusers, and on the vertical axis, we increase the optical thickness. And as you can see here, as we increase the optical thickness, we actually have brighter highlights. And again, this is something that we aim for. We do a similar experiment, but instead, in the vertical axis, instead of the optical thickness, we change the platelet roughness. And interesting, this also, well, as expected, more than interesting, this was expected, these affect the highlights, but in a different way. Specifically, increasing the thickness, increase the brightness of the highlights, Meanwhile, changing the platelet roughness increase the the shape of the highlights itself. And this is interesting because it kind of correlates with how people perceive glossiness. So we also explore how single-lobed and two-lobed phase function affect the final appearance. So we have concentration on the horizontal and optical thickness in the vertical axis, and these two, this one is obtained using single-lobe diffusers, and this other image using two-lobe diffusers. As you can see, having two-lobe diffusers creates more saturated colors and at the same time a more metallic look. Finally, we also want to explore the effects of matching the underlying skin hue, because as I was saying before, foundation, the main goal of foundation is to create an even layer that sort of matches the underlying skin. And so we wanted to explore if we are able to replicate this effect. In this case, we have 4 different types of foundation colors, and we have 4 types of different skins. And as you can see, if the foundation does not match the underlying skin, it's more prone to be more visible. So the limitations of our model is that we have tested only for foundation cosmetics. We have never ventured and tried using it for simulating lipsticks, eyeshadows, or highlighters. And we were also not able to replicate some behaviors. For example, this dark area here, we were not able to reproduce it with our model. And also this darker area here, we were not also able to reproduce it with our model. But overall, given the simplicity of our model and the fact that even with this simple setup, we are able to reproduce pretty well data, I think it's still a good approach. So in conclusions, we provide a model for reproducing foundation layers. We were able to reproduce dewy and matte appearances and in a continuous way. And then we also are able to reproduce this increase in reflectance phenomenon, and then also the stacking of multiple layers, which is what I'm showing here. So we have a foundation layer here, and on top of this, we add another bronze layer. And this is how they look. So, okay. So that was it. Thank you for your attention.